Hello everyone, welcome back to our channel. Today we are going to continuing to talk about message queue, especially how to design a message queue based on the Kafka product. Okay, so in previous video we talked about the basic concepts in Kafka message queue, which is topic, producer, message queue broker, and consumer. We also talked about on a single node or a single machine of a message queue broker, how it receives write request from the producer and how the consumer read the next available data, message data, and consume it, right? And we also talk about the second file and also talk about the index file to achieve faster search within the file, right? Cool. Now in this video, we are going to talk about how the message queue works in a distributed system, which means if we have multiple message queue broker, how does it work, right? So specifically with distributed system with multiple machines or multiple nodes, we want to achieve two things, right? One is high availability, the second one is high scalability. So now let's talk about with multiple machines of the message queue brokers, how we can achieve high scalability first. Okay, cool. So now let's first talk about how to achieve high scalability. Okay, cool. So if you remember the knowledge we talked about in our previous YouTube video, which is high scalability, right? So we can achieve this by partitioning, right? So if you can't remember the related knowledge, I highly suggest you to go back to the previous video, which I added link below this video, so you can check it again to see what is partitioning and how we usually do partitioning. Okay, so I will not repeat those here, I will just use those knowledge here. Okay, so basically we use partitioning to be more specific. So for each topic, okay, so let's say for topic new uploaded video, okay, so for this topic we will have several partitions of the queue for this topic. Okay, so let's say we have 5 partitions. Okay, let's say we have maybe not 5, let's say we have 100 partitions. Okay, because it's more similar to what the real case is. Okay, so we have another 95 partitions. Okay, so this is partition 1, and this is partition 2, and there's other partitions. Okay, cool. So basically when a new message of new uploaded video topic is generated, it will be put into one of these partitions. Okay, and these partitions will be on different broker machines. Okay, so for example, maybe partition 1 and partition 2, they are on broker 1 machine, and for partition 3 and partition 4, they are on broker 2 machine. Okay, so usually the workflow is like this. Okay, so first producer. Okay, so cool. So here is a producer. Okay, so now it has a new message, which is new uploaded video. Okay, so usually for each message we must have a key in Kafka. Okay, so for each message we must have a key. So let's say for this new uploaded video message, there is a key. It could be the video ID. Okay, or it could be a combination between the user ID and video ID. Okay, it's based on your design, right? But anyway, it's a key that you can use, right? And also there is this topic, right, which is new uploaded video, and also timestamp, and also there is body data, right, which could be JSON or any other type of data. Okay, cool. So now we have this message. Okay, so basically on the producer, there is a library. There is a message queue library, right? So it could be a Java library, it could be a Golang library, it could be C++ library, but basically it's a client library, right? So that library will calculate which partition this data should be sent to based on the key. So one way we can do this is based on consistent hashing, right? So which we already explained in details in our related videos, which is high scalability, right? So still, you can go back to that video to check what is consistent hashing, right? So, but anyway, so based on consistent hashing algorithm, so the client library can know based on this key, which partition it can go to. Okay, so let's say we know this message should go to partition 2. Okay, and also based on consistent hashing, we also know broker 1 is the one which hosts this partition 2 data, right? So then this data will be just, this message will be just sent to broker 1. Okay, cool. And no matter what algorithm you use to assign the partitions, for example, we talked about we could use consistent hashing to do this partition and to calculate which partition the message should go to, right? So yeah, you could use consistent hashing, or you could use any other algorithm you could use, right? So, but no matter which algorithm you use, we need a place to remember the consistent hashing result, which is which broker has which partitions, right? So all those information in Kafka system, it's stored in a system, in a component, which is called Zookeeper. Okay, so we have a Zookeeper here. Okay, so what is Zookeeper? You can think Zookeeper is a centralized system which can store all the metadata and all the configurations in our system. Okay, so and all the clients, for example, all the producers, all the brokers here can connect to this Zookeeper to get the configurations. Okay, so in our case, we want to store which broker has which partitions, right? So they are stored in this Zookeeper. Okay, cool. So for example, in this Zookeeper, we could have data records like this. Okay, so for partition 1, we have broker 1 to store the partition, and for partition 2, okay, we have broker 1. Okay, and for partition 3, it's stored on broker 2 machine. Okay, and we also have other configurations here. Okay, so Zookeeper keeps all this information. Okay, and the producer and all the brokers, they can get this partition information from the Zookeeper. Okay, and also whenever a broker crashes, we need to do rehashing, right, based on the consistent hashing algorithm. And Zookeeper will detect the failure of a node or some events, okay, and it will notify all the producers and notify the brokers, okay, some node is failed, and then all of these clients will do rehashing, so they know the correct partitions and the correct brokers to send requests to after the node failure. Okay, so we will have a separate video to talk about how Zookeeper works, but for now you just remember it's a system which stores all the configurations of the system, and in our case it stores the partition information, especially on which partition is stored on which broker. Okay, cool. So this is how we achieve high scalability through partition, right? So Now let's talk about consumer. So we have consumers on this side. Okay, so let's say, remember consumers, it's also a distributed system, right? So for example, maybe our consumer is subtitle generation service. Okay, so there could be multiple machines. Okay, for example, there could be 100 different machines in this subtitle generation service. Okay, so let's say this is consumer one, and this is consumer two, right? And this is consumer three. Okay, and possibly there could be, let's say there are 20 consumers in this service. Okay, cool. And also for the partitions here, we have, let's say 100 partitions. Okay, cool. So now we have different consumers for this subtitle generation service, right? So each consumer needs to grab a message from some partitions, right? So how do we know which consumer gets data from which partition? Okay, so it's also through the Zookeeper, and also you could use consistent hashing or any other algorithm to decide, okay, which consumer gets data from which partitions, right? So it's also stored in Zookeeper. Okay, similar mechanism with producer side. Okay, so the interesting thing is that we have to guarantee no two consumers will get the same data, right? So especially, for example, if both consumers, consumer one and consumer two, they are consumer data from this partition one, then there is a big problem. That's because they could consume the same data, right? So let's say we have a new message. We have a message which is new video uploaded here. Okay, so if both consumer one and consumer two, they get data from this partition one, then they can get the same data, right? Then both consumer one and consumer two will generate subtitles for this event, right? So here, there's not, maybe it will not cause problem because it's just a waste of resource, right? You use the two different nodes to do the same thing, to do the same operations and generate the same results, which is you wasted the resource, right? But there's no problem because it still generates the same data. However, let's say we have some other service which is pay to some user. Okay, so if both consumer gets the same event, get the same message, you will double pay that person, right? Which is definitely a huge problem, right? So for this subtitle generation service, for the consumers in the same service, we shouldn't let them connect to the same partition. We shouldn't let them consume data from the same partition, right? So to avoid this, we have to make sure each consumer will consume different partitions and there is no overlap, right? And this also implies, okay, we should have more partitions than consumer, right? So why? Okay, let's explain this. Let's say in some extreme case, we only have one partition, okay? So let's say we only have one partition, which is partition one. In that case, it means in order, let's say we want to make sure all consumers will consume some content because we want to maximize our computing power, right? So because we only have one partition, then all these consumers will be connected to this partition, right? To the same partition, and definitely will consume the same data, right? Which we want to avoid, right? So we cannot have fewer partitions than consumers, right? So we could have equal number, right? So basically for, let's say we have 100 partitions and we could also have 100 consumers, right? Then that's perfect. So each consumer just consumes data from one partition, right? So we could also say we have fewer consumers than partitions, right? So we have more partitions than consumers. Then it's also good because that means, for example, in this case, each consumer, they just need to consume 5 of the partitions and there could be no overlap, right? So this is good. So basically in Kafka, the basic design is that we should have more partitions for a topic should be larger or equal than the number of consumers for a topic. Okay. So this is a basic design principle in Kafka. Okay, cool. Okay, so this is, we talked about there could be multiple consumers for this consumer one, for this subtitle generation services, right? And the reason why we want to have this rule is because we don't want two consumers in the same service consume the same data, right? However, we could have other services, right? So we could also have maybe people recognition service, right? It also has many consumers, right? Okay, cool. And as we talked, the number of consumers in this service must be small or equal to the number of partitions of the topic, right? However, the consumers in two different services, they should be able to consume the same event, right? The same message, right? So, and there's no problem. So for example, let's say we have a message here, which is new uploaded video, and it's for a specific video ID, right? Then we should be there, we should allow different services to consume this same data, right? Because they are doing different things. They will not cause any problem, right? So definitely, for example, for subtitle generation, we should allow it to generate the subtitle for this video, right? And also for people recognition service, we should allow it to consume this same video message, right? So we can generate people recognition result for this same video. So yes, so actually we need to make this clear. So the number of partitions for a topic should be larger than the number of consumers for a topic. We should change this to of consumers in the same service, right, for a topic. What does this mean? This means for subtitle generation service, the consumer number should be less or equal than the partition number. And for people recognition service, the number of consumers in it should be equal or less than the partitions of this topic, right? Cool. And in Kafka, each service has a name. We call each service here as a consumer group. Okay? So basically we can have a consumer group for subtitle generation service, and it has these consumers. And for this people recognition service, we could create 20 consumers, and they are grouped together under this consumer group. Okay, so, and within each consumer group, the number of consumers should satisfy this condition, right? To avoid the two consumers in the same consumer group will consume the same data. Okay, cool. This is how we achieve high availability through partitioning, right? And we also have another problem, which is high availability, right? Okay, cool. And as we talked in our previous video on how to achieve high availability, also I attached the link of that video in this video's summary. Okay, so you can check it out. And also for high availability, we usually do data replication, right? Data replication. Okay, so what does this mean? Okay, cool. So basically it means, okay, so let's copy this, okay? Here, okay, cool. So based on what we talked about, so we will use consistent hashing or any algorithm we have to duplicate this. Okay, let's also copy the Zookeeper here. Okay, cool. So basically what we will do is we need to replicate the data on our partition to other brokers. So for example, let's say for this producer, we have a new message we want to store, we want to put into the queue for the topic. So based on the consistent hashing algorithm, okay, we can see we need to put it into partition 1, okay? And partition 1 is on broker 1, no problem. We just send request to broker 1. However, this broker 1 can easily crash, right? So if it crashes, then we lose the data here, right? So that's why then it means we don't have any availability achieved, right? So in order to have availability, which means in order to have high availability, which means even some components, some machines, some brokers crashes, then we still don't lose data, right? So we use data replication to do that, which means, okay, so for each partition, we actually store it to multiple brokers, okay? So for example, for this partition 1, okay, based on consistent hashing, we know it needs to be stored on this broker 1, and we call this broker 1 as primary node, okay, or primary broker. Okay, but at the same time, we also specify it will also be stored on broker 4, okay, and broker 7. Okay, cool. And for partition 2, we know based on consistent hashing, it should be stored on this broker 1. Okay, and similarly, this broker 1 is called primary broker, and let's say it's also need to be replicated on the broker 4 and the broker 7. Okay, and for partition 3, the primary broker should be broker 2, and we also specify it need to be replicated on broker 10 and broker 12. Okay, so similarly for other partitions, we also specify what other brokers we need to store to replicate the data to. Okay, so now after we store this new message on partition 1, okay, so we just store it here and then we return a success response to this producer. Okay, and also the other broker. So for example, for partition 1, we also know the data, yes, we stored the data on this broker 1, but there is data, the data needs to be replicated to the broker 4 and the broker 7. Okay, so in this, to achieve this replication, so broker 4, okay, let's say we have broker 4 and broker 7. Okay, they are also consumers. Okay, so they are special consumer, of course. So these brokers will also be consumers and they consume data from partition 1. Okay, so basically broker 4 and broker 7, they are machines. They are you can also consider them as consumer nodes. Okay, so broker 7 is also a consumer node. So basically these two brokers, okay, they will be connected to this partition 1, which is on broker 1. Okay, so they will pull data from partition 1. So they will get the data into themselves, which means we replicated the data to broker 4 and broker 7. Okay, so the data is replicated on broker 4 and broker 7 through this consumer mode. Okay, so this is how we achieve replication. So now you can see the same data besides on the primary broker, which is broker 1, now it's also on broker 4 and broker 7. Okay, cool. And let's say broker 1 crashes and never came back. No problem. We still have the data on broker 4 and broker 7. So we can continue to serve all the consumers from these two brokers. So basically, a Zookeeper will elect one of the brokers as the new primary broker. How to elect, we will explain it in later videos on the design of Zookeeper. But let's say broker 4 now becomes the primary broker. So here broker 1 crashes, okay? Broker 1 crashes, and now broker 4 is elected as a new primary broker for partition 1 and partition 2. Okay, so now this change will be notified to all the producers and all the other brokers. Okay, so now for the new producer, for a new message produced by a producer, it will know, okay, now the new partition, now for partition 1 and partition 2, now they are on broker 4 now. So the request will be instead sent to broker 4. And also similarly, broker 7 will be the consumer which will be connected to broker 4 now, right? So and it will pull and replicate the events from broker 4 now. Cool. So this is how we achieve data replication in Kafka message queue. Okay. So yeah, basically we covered all the concepts and workflows in Kafka message queue. So let's have a retrospect. So in the first video, we talked about the 4 concepts in Kafka message queue, which is producer, message queue, consumer, and topic. We also talk about on a single machine or on a single message queue broker, how it stores the messages and how the consumer stores the messages efficiently, right? With index file and with segment file and also with sequential read and write. And also in part 2, in this video, we talked about how to achieve high scalability through partitioning, right? And also the partitioning information is stored on Zookeeper. And also how consumers can consume the data from different partitions without consuming the same content on 2 different consumers, right? But different services can consume the same data, right? And the different service in Kafka is actually called consumer group. And we also talked about how to achieve high availability, which is through data replication. So the message will be replicated on different machines. One of the broker machine is called primary machine, and the other machines, they will pull data as a consumer from the primary machine, from the primary broker. And this is how we achieve replication, which achieved high availability. Cool. So hopefully you enjoyed this video, and if you like this channel, please subscribe to it, and I really appreciate your support. Thank you. See you next time.